Hello everyone, welcome to another episode of Material Matrix. Welcome. Today we're demystifying PRISM theory for polymer systems, we'll explore how pyPRISM transforms this complex framework into an accessible, user-friendly tool, democratizing advanced polymer science and accelerating material innovation. Stay tuned. Can you just explain the significance of polymer interaction, site model PRISM theory, in understanding the behavior of liquid-like polymer systems and how it differs from other theories in polymer science?
The polymer reference interaction site model. So PRISM theory is kind of like a detailed map for understanding how different parts of a liquid, like polymer system, interact with each other. Imagine a busy playground where kids like the polymer chains are running around and playing together. PRISM helps us see where they are likely to gather, sort of how they move and how they interact with one another. This theory is significant because it describes the structure and thermodynamics, essentially the energy and behavior of various types of polymer systems, including things like melts, blends, solutions, and nanocomposites. It really focuses on the sites on the polymer chains, which are like specific spots on each kid where they might hold hands or play tag with others. What sets PRISM apart from other theories is that it provides a detailed view of these spatial correlations, allowing scientists to predict how the polymers will behave under different conditions. However, it hasn't been just as widely used as some sort of other methods, like self-consistent field theory, mainly because those alternatives often have more accessible tools available for researchers to use. In summary, PRISM is a powerful tool for exploring the interactions in liquid-like polymers, but it still faces some kind of challenges in terms of accessibility compared to other theories.
What are some of the specific challenges or complexities that researchers face when applying PRISM theory, and how does the pyPRISM framework address these issues to make the theory more accessible for practical use?
Researchers face specific challenges when applying PRISM theory. First, understanding and numerically solving the theory can be quite complex, like trying to navigate a tricky maze with so many twists and turns. So this complexity can lead to mistakes if someone isn't careful. Second, many potential users of PRISM theory may not have a strong programming background, making it hard for them to use the tools effectively. So the pyPRISM framework addresses these challenges by providing a kind of user-friendly environment. It acts like a helpful guide through the maze of offering a simple scripting interface that makes it easier to set up and solve the whole theory without getting lost in the details. So, additionally, to support users, pyPRISM comes with comprehensive documentation and tutorials, which are like instruction manuals that explain how to use the tool, like step by step. This way, even those who aren't experts in programming can still successfully apply PRISM theory in their research. In summary, pyPRISM aims to lower the barriers and make the powerful PRISM theory more accessible to a wider audience by just simplifying the process and providing educational resources.
Can you elaborate on the specific features of the pyPRISM framework, such as the data structures and numerical optimization routines it provides, and how these components facilitate the calculation of structural and thermodynamic parameters in polymer systems? So
the pyPRISM framework has several specific features that make it easier to calculate structural and thermodynamic parameters in polymer systems, much like having a well-organized toolbox for a dive object. So one of the key components is like the pyPRISM PRISM object, which is like a blueprint for conducting PRISM calculations. So when researchers want to solve this blueprint, they use the kind of solve method. This method acts like a smart assistant that works to minimize any mistakes by adjusting the input until everything fits together perfectly. So once the calculations are done, the optimized results can be sent to a calculator within the framework. So this calculator processes the data and provides various structural and thermodynamic information, helping researchers understand the properties of their polymer systems. The framework also includes data structures like pyPRISM. So development tailor pair table, which helps organize different types of interactions, such as polymer and polymer pestle relationships. So this is similar to how you might organize different tools in a toolbox for easy access. So additionally, pyPRISM uses specialized objects like pyPRISM matrix array to store correlation function. Think of this as a smart notebook that keeps track of all the important numbers and allows for mathematical operations to be performed pretty easily. So overall, the combination of these data structures, numerical optimization routines, and calculators within pyPRISM streamlines the process of applying PRISM theory, making it more efficient and user-friendly for researchers studying polymer systems like...
So how does the extensibility of the pyPRISM framework allow users to implement new theoretical components or adapt it for tasks beyond just traditional PRISM calculations, such as coarse-graining, atomistic simulation force fields, or modeling experimental scattering data?
The extensibility of the pyPRISM framework is like having a customizable toolkit that allows users to add new tools or modify existing ones for different tasks. This flexibility is particularly useful for advanced applications that go beyond just traditional PRISM calculations. So one example is the ability to use PRISM theory for coarse-graining, which is a method that simplifies a detailed atomistic simulation model into a less detailed and less computationally expensive version. This is similar to creating a simplified map that highlights only the main roads instead of just every single street. The pyPRISM framework plans to include utilities that will help users carry out this coarse-graining process pretty effectively. The framework is designed with simplicity in mind, which means that even those who are new to programming can easily extend its capabilities. Like, users can implement new theoretical components, such as closures, potentials, or intermolecular correlation functions by specifying parameters and input correlation functions by name. So this is like adding new features to a game by simply plugging in new codes that fit the existing structure. Furthermore, pyPRISM can be integrated with other simulation engines, allowing it to process outputs from these engines and feed them back into the PRISM, so calculations. So this makes it adaptable for tasks like modeling experimental scattering data, where researchers need to fit their theoretical results to real-world measurements. In summary, the extensibility of pyPRISM empowers users to customize and enhance the framework for various applications, making it a pretty versatile tool for exploring complex polymer systems and beyond.
What are some sort of practical applications or real-world scenarios where the pyPRISM framework has the potential to make a significant impact in polymer science, particularly in the design and development of new materials or nanocomposites, sort of like...
The pyPRISM framework has the potential to make a significant impact in real-world applications within polymer science, particularly in the design and development of new materials and nanocomposites. So, one practical application is actually in the creation of polymer nanocomposites, which are materials made by combining polymers with nanoporosity. These composites can have enhanced properties, such as improved strength, conductivity, or thermal stability. By using pyPRISM, researchers can calculate and predict how these nanoporosities will interact with the polymer chains, helping them design materials with specific desired characteristics. Like, for example, the framework allows scientists to model the properties of a system made of linear polymer chains and spherical nanoporosities, so providing insights into how to optimize the materials performance. So, additionally, as the pyPRISM framework is extended, users can contribute new potentials and correlation functions, making it adaptable for various types of polymer systems. So, this means that as new materials are developed or existing ones are modified, researchers can easily update the framework to explore these changes, leading to faster innovation in material design. So in summary, pyPRISM can significantly impact polymer science by facilitating the development of advanced materials and nanocomposites, making it easier for researchers to understand and optimize the interactions within these pretty complex systems.
In what ways does pyPRISM enhance the accessibility of polymer liquid state theory calculations for researchers who may not have extensive computational expertise? And so how does this democratization of knowledge benefit the field as a whole?
So pyPRISM enhances accessibility to polymer liquid state theory calculations for researchers without extensive computational expertise in several important ways. First, it provides a simple scripting interface, which is like having a user-friendly dashboard for a really complex machine. So this allows researchers to set up and solve PRISM theory calculations without needing to dive deep into complicated programming or computational methods. Second, the framework includes extensive pedagogical materials, such as API documentation and tutorials powered by Jupyter notebooks. These resources serve as guides, helping users learn how to navigate and use the framework effectively, much like having a step-by-step recipe for just cooking a dish. Additionally, the design of pyPRISM's classes and methods is kept simple, making it easier for novice programmers to extend the framework by adding new potentials or correlation functions. So this encourages collaboration and innovation. So as researchers can contribute their own insights and improvements to the tool, the democratization of knowledge that comes from making pyPRISM accessible benefits the whole field as a whole. it enables a broader range of scientists, including those who may not have a strong computational background, so to engage with and utilize advanced theoretical methods. This leads to more diverse contributions and perspectives in polymer science, fostering innovation and accelerating the development of new materials and applications. So in essence, by lowering barriers to entry, pyPRISM helps create a more inclusive and collaborative scientific community.
Well, that brings us to the end of another really fascinating discussion. So thank you all for tuning in. Today, we delve deep into the polymer reference interaction site model, or PRISM theory. We learned how this sort of sophisticated framework provides a detailed understanding of interactions and spatial correlations in liquid-like polymer systems. While its complexity has historically made it challenging for broader adoption, our discussion highlighted how the pyPRISM framework is actually revolutionizing its accessibility. So pyPRISM stands out by offering a user-friendly interface, comprehensive documentation, and robust tools for numerical optimization. This truly empowers researchers, making advanced polymer liquid state theory available to a much wider audience. So we also touched upon its remarkable features like its efficient calculation methods and its extensibility, which allows for advanced applications such as coarse-graining models and the analysis of experimental data. So this adaptability is crucial for accelerating the development of new materials and nanocomposites. Ultimately, pyPRISM isn't just a tool, it's a catalyst for innovation. By democratizing access to this powerful theory, it encourages broader participation in polymer science, so fostering new discoveries and collaborative breakthroughs. Thank you once again for joining us. So we look forward to seeing you next time for another insightful conversation.